All right. Okay. Thank you all for being here today. And thank you for being online, for those of you who are joining virtually. It is my absolute pleasure to welcome Jon Benstead, Dr. Jon Benstead, here today to Cary. Dr. Jon Benstead is an ecosystem ecologist and a full professor at the University of Alabama in the Department of Biological Sciences. He received his PhD from UGA, the University of Georgia, Athens, which is in the Institute of Ecology, now known as the Odum School. Sorry. Typically, his research explores how landscape and climate changes influence community structure and how these changes influence nutrient uptake, decomposition, and energy flows in stream communities. Really impressively, when I look up his publications, it seems that he's done research in every major biome. And so I imagine that, once we find biology out in space, we'll see Jon there too. He recently has been the recipient of many large grants and plays a lead role on many collaborative research teams. Notably, he's well known for the energy and welcoming attitude that he puts into mentoring and elevating graduate students and early career faculty. I know this firsthand. It is an honor to have Jon Benstead with us today, and with that, I'll turn it over to him.
Thank you, Danielle. Can you all hear me? Great. All right. It's wonderful to be here. Thank you very much for the invitation. I postdoced at the Ecosystem Center at MBL, which is a very similar sort of environment, and so it's great to be here. I know a lot of people who've spent time at Cary for short or long periods of time, and but I've never been here, so it's just very nice to finally visit. So thank you very much for the invitation. All right. I'm going to start off just quickly with some acknowledgements and thank the people and institutions who have been instrumental in the work that I'm about to describe, and especially Alex Hurin, who has been my colleague at Alabama for 22, well, I've been working with him for 22 years, even before I got to Alabama. And he and I have been involved in all the work I'll be talking about today, and it's been quite a ride working with Alex, especially up on the North Slope of Alaska. We've had an absolute blast. And then another PI on the work that I'll get to at the end of my seminar today, Carla Atkinson, who's also at Alabama, and then our three fantastic graduate students. Tori, who is a PhD student, and Adam and Annie are both master's students, and they've all been involved in the new project that I'll get to at the end of my seminar. And also I've got to thank all the sources of financial and logistical support. So the work that I'll be talking about today involves a huge amount of logistics, and I really feel very grateful and fortunate to have done the work that I'm going to talk about today, because not many people get to fly around the North Slope of Alaska, especially in the winter, to all the sites that I'll be showing you today. It really is a real privilege to be able to do it. So we couldn't do it without a lot of support from the Office of Polar Programs at NSF and TULIC, where we're based, and the Alaska state agencies who help us with our research, and many other people. Steph Parker and James Ramsey are no longer at Alabama, but they helped us with the first project I'm going to talk in detail about, Ivishak Spring, and so I wanted to thank them. And finally, you already know that I've already mentioned that we fly around, and so dozens of pilots have helped us, but Elaine and Jared have done most of our winter flying, and without their skill and professionalism, we couldn't do this kind of work, and so we really thank them. All right. So I'm also going to start with an announcement today. So it's interesting, actually, to think about the sites I'm going to be describing today in the context of climate change, but I'm not going to do that today. I thought you might need a break and not think about climate change for a little bit. Instead, I'm going to be making you think about something that is 100% natural, I think very fundamental, and something that I personally find very interesting, but it is challenging to work on. So I'll just remind you that seasonality, the seasonality that Earth experiences, is just an accident, right? It's just the fact that the Earth tilts on its axis by 23.5 degrees as it orbits around the sun, and it spins faster than it does that. It's not tidally locked like our moon, and so for all these reasons, we experience seasons, and it didn't have to be like that. Right, but it is, and I like thinking about that, about all the consequences of seasonality. So that's where we're going to start. I'm going to be briefly talking about all the biological consequences of seasonality, and how, importantly, some of the really important drivers of seasonality, the abiotic drivers of seasonality, are coupled in most ecosystems, and why that makes it a bit challenging to tease them apart. And then, of course, we probably guess where I'm going, maybe, which is that Arctic spring-fed streams are exceptions to this rule, and so that makes them really interesting model ecosystems to work on seasonality. And so then I'll talk about two case studies, some quite old data from Ivishak Spring, that I'll run you through, and which will introduce you to the ecology of these systems. And then I'll finish up by talking about a relatively new project, this Friesel-Frammen project, which actually, the fieldwork, we only finished it in August. So this is preliminary data that I'll be showing you at the end. We've got a lot of work still to do. And then finally, I'll finish off with what these spring-fed streams can tell us about seasonality and how it operates in most ecosystems, and how the spring-fed systems are, again, an exception. All right, so let's go back to the consequences of seasonality. Or the biological consequences of seasonality, we can really, I think, distinguish them, distinguish between what I would call the proximate and the ultimate drivers of seasonality. So these are the sort of what I would describe as the proximate drivers of seasonality. In other words, all the evolved responses of Earth's biota to the abiotic drivers that change throughout the year. So I'm thinking about things like life cycles, the patterns in phenology that we see play out at large spatial scales. Those are all evolved responses to seasonality, and of course they're a very important component of it. But I would argue that they're proximate. They're evolved responses to what I'll call the ultimate drivers of seasonality, which is the way that light and temperature swings through the year as a consequence of seasonality, and especially, of course, the important drivers of light and temperature, and how those play out can play out at large spatial scales. And so just as an example is just a 1-year snippet from the Keeling curve here, from the familiar Keeling curve here, showing how the joint effects of light and temperature are manifested at very large spatial scales. So of course, the Keeling curve is basically showing you the net balance of photosynthesis and respiration over a large swath of the northern hemisphere. That's essentially what it's showing us, and how respiration exceeds photosynthesis during the winter, and then how CO2 is then drawn down as photosynthesis becomes more important than respiration. All right, so obviously light and temperature are driving these patterns at large spatial scales, and that's because of the two processes that they drive. All right, so light, as shown here in this example of a PI, a photosynthesis irradiance curve, is driving GPP rates, and so we can expect those to change as light changes through the seasons. And then temperature, of course, is driving the rate at which ectothermic consumers are metabolizing, shown here, formalized in metabolic theory. And so it shows how mass-corrected metabolic rates here change with temperature, shown in a rather confusing inverse scale here. but that's how they do it. So showing how amongst different classes of ectothermic consumers across the tree of life show this universal temperature dependence. As temperature goes up, going this way on this plot, then respirational metabolic rates goes up. All right, so light and temperature are going up and down through the seasons, and they are driving rates of photosynthesis and rates of metabolism, respectively, at large spatial scales. And light and temperature, again, are coupled and cycling through the seasons together. And it doesn't matter whether you're low latitudes near the tropics, they're going to cycle together, or if you're at higher latitudes, they're still going to cycle together, but the amplitude is going to be greater. And so the significance of that, of course, is that light is driving GPP through the seasons, and temperature is driving the energy demand from via metabolism of ectothermic consumers. And so they're also going to be describing these coupled cycles together. All right? Okay. So, again, the significance of that is in summer, when temperatures are high and the respirational metabolic rates of ectothermic consumers are also high, and the potential demand for energy is high, then those are all matched in the summer because light is high, and so are rates of GPP. And then in the winter, when light is low, and so rates of GPP are relatively low, then those are matched also in the winter by low demand that's driven by relatively low temperatures. And so this is how most ecosystems operate. And of course, the significance of that is that at any point in time in the year, there is matched energy supply and demand. And so that leads to some sort of modulation of energy demand relative to supply through the year, all right? Which can presumably confer some sort of stability in food webs. All right, so I'm positing that that's how most ecosystems operate. You might be able to guess that I'm going to argue that spring-fed streams, especially at high latitudes, do not operate like this. And that's why we work in them. And so, in case you're not familiar with the existence of these sorts of systems, here we are up in Alaska, up here. So this is the north slope of Alaska. And this map just shows the locations of all the known cool and hot springs that are associated with the Brooks Range. And you can see most of them are spread around the eastern end of, eastern end of the Brooks Range. And but they are widespread and quite common, and very interesting places to work, in case you don't know how they operate. So there are various mechanisms by which you can get perennially flowing springs on the north slope, but most of them are associated with recharge areas that may even be, this is the Brooks Range here, so we've got the north slope on this side, and so many of them are have been recharged from areas to the south of the Brooks Range, actually. But this is old water. Much of the precipitation that feeds the springs that eventually emerge, the water is centuries to millennia old. And it's associated with a geological stratum called the Lisbon limestone, and the faults that run through that stratum. And those provide the plumbing by which water that may have fallen south of the Brooks Range a very long time ago filters down through the limestone, is warmed as it does so, and the degree of warming is presumably driven by the depth at which it flows through. And then it eventually emerges in springs that flow perennially, all right? Unlike most shallow running water habitats on the North Slope that freeze, all right? These things flow all year round. And because they flow all year round, even through the winter, what is going on? Then that water eventually cools and freezes and forms these accumulations of ice called alphice, which may be very, very large, hundreds of hectares in extent and meters thick. And those alphice eventually thaw during the summer. And sometimes they're around still by the end of the summer, but greatly reduced in extent. But they're also very interesting. But I'm not going to talk about the alphice. I'm going to talk about this part of the spring-fed streams, these perennially flowing, that emerge at different temperatures across the Brooks Range. All right, that means that these spring-fed streams, which are embedded in this high latitude, highly seasonal environment, experience light temperature regimes which are completely uncoupled, unlike most ecosystems. All right, so here's one of the sites I'll be talking about, Ivishak Spring. So this picture was taken on a day in January when the air temperature was 40 below, but the stream was flowing quite happily at 5 degrees. All right, and so they definitely have uncoupled temperature light regimes. All right, that look like this as opposed to our previous conceptual model. All right, so they might cool a little in the winter, but hardly at all. And so that means that they experience really very pronounced cycles in light and gross primary production in the stream. But the potential energetic demand from the community of ectothermic consumers is essentially going to be a flat line because of the temperature. Right? So that makes them very interesting systems to work in, especially with regard to energy flow through food webs. Right? So there's the potential for a real heavy, very significant energy deficit in the winter. If you're an ectothermic consumer and your respiration rate is the same in January as it is in June, but you've got nothing to eat because there's nothing being fixed at the base of the food web, then that poses considerable challenges. All right. All right, so this is what the data actually look like. So it really does look like this. All right. It really does look like this. These are real data from Ivishak. All right, so I've got no axes on here because I was just trying to make it look similar to the conceptual model. But just for context, so we're going from about 2 or 3 hours of twilight here at the depth of winter, near the winter solstice here, to obviously 24 hours of light in June. And there's some gradient, a diel gradient in light, of course, because the sun's still going up and down. It's not going below the horizon, but you've still got some variation. But you've got 24 hours of light here, right? For context here, this range in temperature here is 2 degrees, all right, from about 5 to 7 degrees over the course of the year. And remember that the air temperature is swinging by 70 degrees or more over the course of the year. All right, so that makes them, I think, really interesting and compelling systems to work on, to use for work on the seasonality of energy flow through food webs. So that's what we've been working on principally for the last 10 or 15 years, off and on. But of course, they're also, these springs are really amazing places biologically that are interesting just because they're so different from the rest of the landscape in which they're embedded, and their natural history is just so interesting. So I wanted also to tell you a little bit about that. So if any of you have been up on the North Slope of Alaska, you'll know that most of it is tundra. There are trees there, but they're about this high, right? Most of them anyway. And if you ever go up there in the summer, then the best thing to do if you've never seen tundra is to immediately go flat on your face and just look at it really close up, because there are all these beautiful little trees in there, but they're about this high. Of course, there are taller trees, lots of willows, and you may know that there's increased shrubbification on the North Slope, so willows are spreading and getting bigger. But when you go to a spring, you can actually spot springs from the air as you fly through just by looking for poplar groves, because balsam poplar really only grows in these large groves near springs because it needs a big thaw bulb to grow. So these are big trees. They're 40, 45 feet in height before eventually they're usually killed by frost or snow. But it's cool to walk around these areas, because it's sometimes hard to believe you're on the North Slope as you walk through these woods. So there's nice poplar groves. They have really quite distinct benthic communities. So remember, these are the only shallow flowing habitats up there on the North Slope in the winter. 99% of stream kilometers freezes solid. And so these habitats represent the only place where many taxa that cannot tolerate freezing, either as eggs or larvae, can live. And so we've got lots of insects that cannot tolerate freezing that we only find in the spring. So things like this big pelodid stonefly here, this is Isoperla. This is a species that can't tolerate freezing, so we only find it in the springs. And of course they are springs, and so they have constant flow. They're very low disturbance, so we have very heavy cover of bryophytes and lots of biomass, and they're very productive in the summer. So quite unusual for Arctic springs for that reason too. All right, char. So this is a species I'll be talking about quite a bit today. So these are, for the most part, Dollyvarden char are migratory on the North Slope. So the adults spawn in large rivers which receive spring water inputs, and the eggs hatch over the winter, and then the young end up in spring-fed habitats. And again, that's the only place where they can spend their juvenile stages. So they're typically there for 2 years or so until they get big enough to swim downstream and go out into the Beaufort Sea, where they spend their some period as adults before they return to spawn. So these spring environments are absolutely essential as juvenile habitat for Dollyvarden char. And they are beautiful little fish. You can see some examples from some of our systems. Actually, one of the sites I'll be talking about, Sadler Rochit, the char population there is resident. It doesn't migrate. So that's slightly unusual. All right. And then two other species I just wanted to highlight. So many of you will be familiar with both these species. They're not that unusual, American dippers and the river otter here. But the springs are the only place where you find dippers on the whole of the North Slope. And they're there year round, right? So you can be walking around in the winter when it's 40 below, and the dippers will be flying up and down the springs, and they breed there, raise their young there in the summer. And so it's very cool to see them there, and they're the only place. And then river otters, another common species here, not that unusual, but there were vanishingly few records of river otters on the North Slope before we started. Now we know that there are otters at least 2 of our sites, which is also really amazing. And these things are also there all year round. And it's an incredibly harsh environment. But they have somehow found these springs, which are scattered over quite large areas, and managed to maintain populations in there. And these are 2, obviously, these are reliant on stream production, and so are important predators in our systems. All right. So I'm going to start telling you a bit more about Ivishak, which is the spring stream that we started working at back in 2007, 2008. Here's where it is. So some of you may be familiar with Tulik. So this is where we're always based, of course, because there's only one road that goes up through the North Slope from Fairbanks up to Prudhoe Bay. And so Tulik's right here. And Ivishak Spring is on the Ivishak River here. So this is a big braided North Slope river that eventually flows into the Sagamanatuk up here. And there are lots of springs around here. So this will be an important highway for char as they go up and down to spawn. And so many of them would spawn around here. So this is what it looks like. So the spring emerges on a fairly nondescript talus slope up here, and here's the top orifice of the spring. We've had data loggers in there for 15 years now. It is a flat line, 7.41 degrees every day of the year, and so incredibly stable temperature. So it flows down the talus slope and then forms this very nice, well-defined channel. Oh. and so it's that reach immediately below the orifice, about 250 meters, that we have studied in a lot of detail. All right, so now I'm going to show you some data. All right. And so here's some ecosystem metabolism data from Ivishak. And so we've got GPP at the top here, gross primary production. And this is actually quite productive if you knew anything about gross primary production, especially for an Arctic stream. But we can see we're going through, we've got about 2.5 years of data here. So here's summer, right, winter, summer, about what you would expect based on the light environment that I have described. And then below we've got ecosystem respiration. You can see it's more or less a mirror image, which tells you that the respiration of this system is pretty much fueled by GPP. Here's some other ways of looking at these data. So we've got light down here, photosynthetically active radiation, and we're going from the winter here, obviously, when the lights are out, to the summer when we've got 24 hours light. So this very strong relationship that you might expect. We can also plot GPP and ER together to see what that looks like. And you could see another strong linear relationship. Obviously, it doesn't hit the y-axis at the origin here. So there's some kind of subsidy available for ecosystem respiration in the system. It's not we don't know exactly what that is, but it's likely to be DOC from the surrounding catchment. I've told you there are trees, and then we've got a small poplar grove at Ivishak, but it's probably not contributing that much in the way of coarse particulate organic matter. So I don't think that's what it is. But there is some carbon subsidy that's keeping respiration going, even when the lights are out. But it's not particularly significant. All right, so we've got definite evidence for some sort of energy deficit because, obviously, our GPP and ER is looking something like this, all right, where there's a very tight coupling between GPP and ER, in the face of this essentially flat temperature line that carries on all the way through the winter. All right, so that looks like there's definitely scope for a big energy deficit, and so that raises the question of what's going on with the rest of the food web that I've described briefly. I'm mostly interested in how energy flows through food webs, not just at the bottom of the food web, and spend a lot of time trying to tease that apart. So what would we expect if we were able to, if we do measure trophic level production or production at higher trophic levels. I've already described to you that there's this big discrepancy between primary production in the winter and the summer that's driven by light. And so we might expect that just to follow through all the levels of the food web, with there being large flows in the summer driven by high light and high GPP, and then everything pretty much crashing down. Unless there's some kind of subsidy to the consumers, everything's going to crash in the winter. And remember, they're all being maintained at the same temperature. Their metabolic rate potentially is the same in January as it is in June, which is going to exacerbate this. All right. Okay, the only way to test hypotheses like this is to do the work. and this is what most people don't do, because it takes a lot of work. So to get secondary production, getting primary production these days is pretty easy. Just stick some mini dots in the stream, get the oxygen data, and then run it through something like stream metabolizer, and boom, you've got your primary production and your ecosystem respiration in a relatively short period of time. Secondary production, not so much. Right, there is no easy way to get secondary production. You need to measure mean biomass over some interval. You need to match that with an interval growth rate. You usually need to do that for every size class in each taxon. That's a huge amount of work, right? But that's what we did. It's a lot of work in the summer. It's even worse in the winter. So here I am with a big smile on my face. You can see there on a particularly cold day at Sadler Roach It, tagging and weighing fish, which is one of the things that you need to do. Right, so that's lots of work. It's lots of work in the field, and it's even more when you bring everything back to the lab, when you've got to sort it all, especially the macroinvertebrates. But we did it. So here's what we find. So here's some data from the primary consumers. So this would be the second trophic level in the food web. And so things like midges here. So these are daily production values over the course of the study. And you can see, well, this looks pretty similar to the primary production here. Another way of looking at that is by looking at daily P2B. So that's a production to biomass ratio. So you can think of that as sort of an analog to a growth rate, but at the population level. It's the rate at which the biomass is turning over, essentially. So if your biomass is also changing through the course of the year, then you might expect even more pronounced signals, and that's what we see. All right? So really big swings. And we can also plot the production data for the primary consumers against daily GBP. Again, this is something else that you rarely see in the literature. Lots of data like this, not so many data like this that are matched in the same system. But when you do that, often you see something like this, but it's particularly pronounced at Ivishak because of the really tight coupling between the in situ primary production in the stream through the year and all the grazing that's being done by and subsequent production that's being done by the primary consumers. We can look at the next level of the food web. So here are the secondary consumers, so things like that Isoperla stonefly, and they show similar patterns. It's a bit more muted, which you might expect because production of these invertebrate predators is likely to be lagged behind that of the prey that they're consuming. So you might expect both rates of daily production and daily P2B to show the same patterns, but a bit more noisy, and that's what we see. If you move up to the top aquatic predator, which is the Dollyvarden char, then again we see the same sorts of patterns. And so here are our individual growth rates for 151 recaptured char. And so each of these lines starts when the fish was first captured and ends where it was recaptured. And then the position on the x-axis is its specific growth rate over that period at which it was at large in the system. So 151 recaptures shown here. And you can see really big swings. So in the winter, many of these fish are losing mass. All right? So think about the twin consequences of not having very much to eat and being maintained at this relatively high body temperature, and what effect that has on their growth rate. And then, of course, you can see some screaming high growth rates in the summer when there's plenty to eat, and I'll show you some potential mechanisms for that in a moment. We can also look at what's called the condition factor of the char. So this is basically a measure of how fat they are or how much they weigh for their length. And so on this plot here, if you're at 1, then you're at the mean mass for your length. If you're above 1, then you're fatter. If you're below 1, you're skinny for the population. And again, that shows the same pattern. So these fish really are losing a lot of condition, often losing mass during the winter, during this period of famine. And then here's the equivalent daily production values and daily P2B values for the char. And here's a mechanism for the patterns that we see in the char. So here are the top 5 categories of prey in their guts. So we've got Batis, a mayfly here, Ecclesiomyia, which is a little caddisfly, a terrestrial sort of grab bag here, both true terrestrial insects and adult aquatic insects, and then 2 stoneflies, the one I've talked about, and Zapata is another stonefly. You can see that in the summer, Batis is really important. So Batis are abundant, and they frequently drift, and they're really important char prey. And this is what happens to Batis over the course of the year. So the black symbols here are in the winter, and the yellow symbols are in the summer. And what we've got here is the mean individual mass of mayflies, their biomass on the stream bed, and the biomass in char guts. And you can see the Batis are there all year round, but they're only really growing in the summer. Right? So in the winter, they're just hanging out. And they're quite small, and they're not growing, right? And then when the lights come back on and the diatoms start growing, then they start growing, and you see their biomass go up in the benthos, and the char just start nailing them, all right? Both in the drift and Dolly Varden, actually, I don't know whether you noticed that they've got quite underslung mouths for salmonids. They actually spend quite a lot of time feeding benthically. They're not just drift feeders. All right, so it's maybe not surprising, given data like this, that the char don't do so very well in the winter. All right, so here's a quick summary of our results from Ivishak. These are the old project, the first one we did on the springs up there. So obviously there's a tight linkage between light and food web production at every trophic level I've shown. And at least in the char, you see these really steep declines in the winter that are driven, again, by the lack of prey, and presumably also there's a penalty incurred by the relatively high temperatures. You know, they have to be in these non-freezing flowing habitats. They don't have any choice, but they may incur a penalty by staying there in the winter because their metabolic rates are elevated. All right, but it's slightly frustrating because we can't manipulate temperature at Ivishak, right? So we actually don't know, okay, what would happen if temperatures were lower? Would they do better in the winter? Or what would happen if temperatures were even higher? Would that mean an even more severe penalty incurred by char? We can't answer a question like that because we've only got a single stream, so it's slightly frustrating. Because any test of that hypothesis, we would need a winter gradient, and that's where we went in our follow-up study, which only just finished. The fieldwork finished in August, which is what we call the freeze or famine project, hopefully for obvious reasons, because they don't have any choice really about where they go, especially the fish. All right, so we found a temperature gradient. So again, we're back on the North Slope here. Here's Ivishak, but we added 4 other sites that vary in temperature. Saviukviak here, Flood Creek, Echuca, which is our coldest stream, and then way over here at Saddle-Rochit. So this is the Saddle-Rochit Mountains. We're only about 20 miles from the Arctic Ocean here. This is the northernmost extent of the Brooks Range. And here's the temperature gradient we got. And so, few things to notice here. We've got a big range. Right, Saddle Roches are really warm. It's a huge spring. It's about 1,000 liters per second, but it comes out at 12 degrees. And it's pretty much a flat line. And then at the other extreme, we've got Echuca here, which is really cold and miserable to work in for that reason, and especially in the winter, because it never gets above 3 degrees. And then here's good old Ivishak here in the middle, what we call our OG site. And, but you all will have noticed there's a bit of an outlier here, Saviukvak. Okay, obviously we didn't have these data when we started. We had some data, mostly, I think it was all from the summer. We were just trying to make our best guess. You know, there aren't lots of data out there on these springs, so we had to make our best guess. We didn't know that Saviukvak was going to do this. So presumably, I think it's interesting. It's kind of a pain for our gradient, but it's interesting. Obviously, that's a spring that's plumbed a little differently from many of the others, and so maybe one day we'll find out why. But the important thing is, you don't see that very well, but at least in the winter, which is what we're interested in, we have a really very nice gradient that we can use to test our hypotheses. So maybe you can't see these boxes, but I've just highlighted the winter period here, when we really do have this very nice gradient. Okay, so we had two goals in this new project. One was actually test this hypothesis. If we can use a temperature gradient, find a temperature gradient, then do we see increasing severity of carbon energy or energy limitation in the winter as temperatures go up? The other thing we wanted to do is to extend our work into new areas. So both Alex and I, we spend most of our time thinking about, well, communities and ecosystems really, every now and then populations. But we don't do very much physiological ecology, but we became very interested in how individual organisms cope with winter. And so we want to extend our work to physiological ecology and look for the different mechanisms by which individual organisms might get through the winter. And so, you know, one of the easiest things to do, especially if you're a fish and highly mobile, is just bug out. You know, look for lower temperatures where you can lower your metabolic rate and lower your metabolic costs. And we actually see some evidence for that, but I won't show you that today, especially in the warmest stream, where the fish do seem to move out in the winter. That's not so much an option for the macroinvertebrates. I guess they could drift out. And then another thing you could do is adjust your metabolic rate. Right, so that requires some form of plasticity, but it's going to be another way of getting through the winter. You can also just stop growing, all right? And I've shown you an example of that in the Batis. They seem to stop growing in the winter when there's nothing to eat. That's one way of getting through the winter. And then there are some more severe mechanisms. You could rely on lipid reserves, or really an extreme mechanism is to start breaking your own muscle down, right? And so we've been using a combination of techniques to get at some of these, which are pretty new to us. So we're doing aquatic respirometry in both the char and macroinvertebrates, or we have been doing it. We can look for cessation of growth quite easily, obviously. We're measuring energy density with a bomb calorimeter and looking at lipid levels. We can also use stable carbon isotopes to look at reductions in lipid, and then we're using stable nitrogen isotope ratios to look for evidence of starvation-induced autophagy. Right, so I've got just some data. Obviously, we only just finished, so we don't have it all. I don't have any ecosystem metabolism data to show you. That's all still in bits, as it were. And then here's a picture Alex sent me yesterday of our pile of coolers that contain all the benthic samples, which are being sorted by an army of undergraduates, but we've got a long way to go. So I don't have that yet, but we get some data quite quickly from the char. And that's actually illustrative, because of course they're on the top of the food chain, at least the aquatic food chain, if you just ignore the dippers and the otters for the moment. They're likely to be integrating lots of what's going on in the food web below them. So they're interesting for that reason. All right, these are really preliminary data. In fact, I got this yesterday. so from my student, and but I still want to show you. So his mass-corrected metabolic rate through the year, and so we actually measured metabolic rate of the char. So well, we can't really see the setup here, but here's a char, look, in a respiration chamber. So this is our setup at Tulik. So we bring fish back and measure respiration rates at different temperatures, and then sadly they'd have to be sacrificed. But we wring every last little bit of data we can out of them, and so they did die for a good cause. But so here's our mass-corrected. So these are respiration rates that are measured at their home temperature, right, through the course of the year, at the temperature of the spring from which they came. And so new, we haven't done any stats or anything like that. But there's definitely signs of plasticity in respiration rates over the course of the year. So this is obviously summer, we've got winter here. So it looks like a hump-shaped relationship here. We don't exactly know why this could be. This could potentially be driven just by fasting, right? So this could be the difference between having some specific dynamic action or the metabolism that's driving digestion of food and not when you're fasting and you've got nothing to eat. Or it could be something more interesting and actually being metabolically plastic over the course of the winter. We also wanted to test plasticity not across streams, but not across seasons, but across streams, right? So there are some hypotheses about plasticity, things like metabolic cold adaptation, so and hypometabolism. So metabolic cold adaptation would occur at this end. So that's the idea that cold adapted organisms can have relatively elevated metabolic rates at low temperatures relative to warm adapted organisms, all right? And there's some evidence for that, all right? Because these are our two warmest streams down here. And then at the other end, you've got hypometabolism, where warm-adapted organisms are able to maintain their metabolic rates at a lower rate at higher temperatures, whereas cold-adapted organisms aren't very good at high temperatures, and so they end up being stressed and having high metabolic rates. So that means that if you combine those two hypotheses, then you'd always expect the cold-adapted organisms to be on top of this graph relative to the warm-adapted organisms. So again, there's some evidence for metabolic cold adaptation over here. It looks a lot more messy up here. Doesn't seem to be much evidence for hypometabolism. All right, here's some growth rates quickly. So we have crunched all the growth rates. So all we're showing here, we've got all 5 streams here, but I'm just highlighting the coldest stream here and the warmest stream. So the blue dots are Echuca, red dots are Saddle Roachit, the warmest stream. And it's kind of interesting because you don't really see much of a pattern there. They're all interspersed all the way through. Again, we're seeing the same sorts of patterns in growth rate through the year as we did at Ivishak, but there doesn't seem to be much of a temperature effect so far. And again, with the condition factor, I told you about condition factor when I was talking about Ivishak, same sort of pattern, right? They're getting fat in the summer, really skinny in the winter. Again, there isn't that much of a pattern, but there is this one. So this is the change in condition factor over the winter, plotted against mean temperature. And so here's our coldest stream, here's our warmest stream. And so there does look like there's a temperature effect on the change in condition factor over the course of the winter, but we really need to dig into the data a bit more. All right, I'm going to finish off by thinking about what we can learn from Arctic Spring streams, which have this unusual, uncoupled light-temperature relationship. So obviously, the value of these really interesting systems are that they offer this ability for us to separate temperature and light, which are coupled in all other ecosystems in a pretty compelling way, because it's really impossible to separate light and temperature, at least at the level I want to work at in real food webs, at relatively large spatial scales. And we can do that with these systems. And I think that makes them very interesting. And obviously, their stable temperatures, for all those reasons, increase the relative severity of energy limitation in the winter, because temperature maintains metabolic rates at the same level as they are in the summer. And so what does that mean about most other ecosystems that look like this, that have coupled light and temperature regimes? Well, I think that might be important in ways that these spring-fed systems kind of illustrate that these coupled cycles in most ecosystems confer some kind of stability, a built-in stability, right, that complements all the other evolved mechanisms of getting through the seasons that we typically study. Things like phenology and life histories, things like acclimation and adaptation that we actually see some evidence for. And something I haven't talked about, which of course is the production and subsequent use of detritus, which, when you think about it, is a consequence of seasonality and is another mechanism by which food webs get through the winter. All right? And I'm going to stop there and take any questions. Chris.
Jon, thanks. Just a cool set of ideas and really amazing study system, and the data, I think you undersold how hard it is to get.
Oh.
It was amazing.
Thank you.
A lot of ideas and questions for you, but one that I was thinking about as you were talking about this possibility that in the warmer spring-fed streams, it's worse to be a char.
Yes.
Because you're at an elevated metabolic rate, so you're depending on something more. I don't know if I'm going to say this intelligently, but it seems like there should be big fitness advantages if you're a diehard into finding the stream that is just warm enough to not freeze during the summer.
Right.
So have you thought of that kind of landscape evolutionary?
Well, yeah, no, we think a lot about it. But obviously that's also going to change through the year, right? Your optimum temperature is going to change through the year. So you'd never be able to find maybe there is, well, I guess there would be an optimum fixed temperature to be at. But the optimal strategy would be to move. Right now, and we do see that. And I was hoping that Alex is working on all the abundance data right now, and I really wanted to show that because at least in our colder stream, Echuca, that at least based on what I remember, the char seemed to move be there in higher numbers in the winter than they were in the summer. And remember that's the stream that's at 3 degrees, 2 or 3 degrees, and then Sadler Rochit, which is our warm one, they definitely seem to move out of that in the winter. There's an added, well, no, it's not a complication, but remember that's also the site where the char population is resident. But that shouldn't matter because we were right at the top of the spring, and it's that area that they seem to move out. And of course, anytime you go downstream from the spring source, it's going to cool because eventually it turns into that ice. So it would be really nice. It would have been great to get a better handle on movement through the year, and we thought about that originally at Ivishak, but it was just, you just can't do everything. So we were lucky, we were really fortunate. That first project at Ivishak, we were actually staying there, so we'd get dropped off all through the year. We'd get dropped off and we'd stay out there for 3 or 4 nights. And that's why the metabolism data, this is before mini dots, so the metabolism data, you probably noticed, are only just for a few days each month. the new project is different. We were only on the ground for a few hours each time, especially in the winter. We'd only be on the ground for 3 hours because that's all we had, and so that does limit the kind of work that we can do. But yeah, it's really interesting to think about the optimal strategies for the char. But movement, I think, is a really important one. Yes.
Well, Chris kind of poached my first question, but I'll let that go. So were you able to do GSI on the fish, gonados, or basically the fecundity proxy measure when they're sacrificed?
Well, so.
Sorry, do you mind just repeating the question?
Oh, so the question is, was I able to do GSI, a gonadosomatic index? So we technically could do that on the fish that we brought back, because all those fish were respirometry, which is only, I think it's a total of 100, because that's all they let us take. But of course, these are juveniles, right? So we might see gonads in the saddle roachet fish because they're residents. But the rest of them, we wouldn't expect to see any gonadal development at all. But what are we going to measure? You know, we're going to measure stable isotopes, lipids. We'll get their otoliths out, energy density. If anybody else has got any other ideas, let me know. They're in the freezer. Yeah, you know, I can understand, you know, the saddle roachet fish, the Alaska Fish and Game are really kind of precious about the saddle roachet fish because they are kind of a special resident population. Of course, the population is absolutely huge. I don't know why they're quite as precious about the others because there's dollyfod and nupsy everywhere on the North Slope, but anyway.
If you had to guess, would you say they're likely to have lower fecundity in that higher temperature?
Ooh, well, it'd be obviously a hard comparison because that's the only one, but they are in the summer, those fish are just in superb condition. I mean, I don't know whether you saw some of the pictures. They are some of the most beautiful fat char you've ever seen. So it would be, I mean, there's very little work done on that resident population. No idea how long they've been locked in there. Presumably since the last ice age, probably. And the reason they can't get downstream is the river, the Saddle Roachet River essentially goes dry, kind of underground for a period of time, so they can't make it out to the Beaufort Sea. So, yeah, it's interesting to think how long that situation has been. But any other questions? Yes.
Sorry, I have another one.
Yeah.
Are you familiar with any equivalent sort of systems on the equator that would allow you sort of to invert it, that would have, you know, the same bright daylight, but it would have temperature?
Well, I imagine, yeah, that's a good question. It'd be hard to get the swings in temperature, I think. I mean, I think you could find places like maybe a glacier-fed stream in Ecuador or something like that, but the temperatures would still be really low, and I don't think you'd get much of a swing. Can anyone else?
Here, yeah, I got a question from the virtual audience here. Alan asks, what is the chemistry of the discharge water in these streams? And are there organisms or DOC in the discharge water?
Are there organisms?
Yes, that's...
I'm pretty sure there aren't very many organisms. That's so for context, the water, we don't know very much about the age of the water in the springs, but there was a paper that came out in PNAS earlier this year that did age the water at Saddle Roachet. So in the winter, it's about the water that discharges from Saddle Roachet is about 10,000 years old, all right? And so it is, It is chemically modified. I'm not quite sure what the person asking the question means by chemistry, but obviously it's chemically modified. It's been in contact with bedrock for a long period of time. Of course, there is some diversity in spring types up there, but Ivishak, if he means sort of nitrogen, phosphorus, and things like that.
I imagine like DIC2 or something like that.
Right. Well, so the DIC is high. It's been flowing through, limestone, and so that's high. Nitrate is probably also of geologic origin and is relatively high for the North Slopes, like 80 micrograms per liter. Phosphorus is low, so that's mostly what I think about.
Yeah, I guess I have yeah, go ahead, Amy.
Yeah, thanks so much for the interesting talk. I was making my brain crunch around thinking about this system. And so I was trying to formulate how to ask this. Maybe it's like building off of what Lauren was just asking at the end there. But thinking about that, a lot of your measures are focusing on how do they survive at these high metabolic costs when it's really cold. And I was curious about whether there's compensatory, like are they growing or doing something extra when it's really good, and so that you have a bigger slope. And so I was trying to track sap, because that seems like it'd be the easiest.
Right.
It does seem like it's doing something different, but I think really going to like the more typical system where people work and seeing comparisons, like are they doing much better? Do they seem like they're doing better? You were describing how fat and happy they were, that made me think that maybe yes.
Yeah, and of course.
In the summer, and then that can compensate.
Yeah, and fish in particular are, well known to engage in compensatory, or what's in the fisheries literature is called catch-up growth. So that's definitely a possibility, but that needs some sort of careful teasing apart to get a catch-up growth, where you need to do the comparison between what it's like to have constant rations and non-constant rations, and but yeah, I mean, fish do that all the time, and so that's highly possible, right? Well, I don't. Yeah, obviously we're bringing those fish back to Tulik. I don't know whether they would ever get permission to take enough, to do. We were able to take 20 from each of our sites. That was it. So, but yeah, it's interesting to think about.
I guess I have one last question,
Yes.
And then we'll wrap it up. But so one of the things I was noticing is the actual temperatures that, I didn't know this ahead of time, the temperatures that you were presenting are actually pretty common groundwater seep temperatures in temperate zones.
Yes.
And so it would be an interesting comparison, I should say, not easy, interesting comparison to look at kind of temperate zone groundwater seeps, and I guess what would be the major differences that you could see between those two zones, and I guess have you thought about that?
Differences in what respect?
Like, I guess why kind of pulling out like what. So obviously it's in this light regime here, what would we think about being kind of interesting in the groundwater, comparing a temperate groundwater seep to these spring seeps, and what could we learn, I guess, more so?
Yeah, well, I think, in many ways they'd operate in a very similar way.
Right.
Except they wouldn't be embedded in such a highly seasonal environment. And depending on the context, they might not be so dependent on summertime in situ primary production. I mean, that's partly what's driving this, right? That they don't receive much in the way of a subsidy, and so that might be a difference. But other than that, I imagine they'd operate in a pretty similar way.
Right. Yeah, and definitely thinking kind of like the mobility, right, factor here. They can't move past a certain point, but there's definitely a little more availability to move. Awesome. Well, thank you so much, Jon. This was really great, and thank you all for attending today.
Thanks, everyone.